In this loan default prediction project, we adopted a series of model training, parameter training, and ensemble learning strategies to maximize the F1 score and continuously improve the performance of the classifier. The specific model improvement process and methodology are summarized as follows. First one is the background and the objective. Loan default prediction is a critical component of financial institutions' risk control systems. Accurately identifying potential default customers can effectively reduce bad debt risks and increase profitability. The objective of this project is to develop a high-performance classifier based on historical loan data to accurately predict loan default risks, with the F1 score as the core evaluation metric. During the initial model testing phase, we considered PyCaret to quickly experiment with various models and obtain performance benchmarks. PyCaret is a tool capable of automating data preprocessing, model selection, and parameter tuning, making it suitable for rapid exploration. However, considering PyCaret's limitations in flexibility for complex and simple models, we ultimately opt to manually turn parameters and construct ensemble models for optimal performance. Then we are talking about data preprocessing. Data analysis revolved that the raw data was of high quality with no missing values. However, there was a class imbalance issue with default samples accounting for approximately 20%. The main data preprocessing steps included first, categorical variable encoding. One hot encoding was applied to prevent ordinal relationships from introducing misleading information. Second is the numerical feature standardization. Numerical variables such as income, loan amount, and credit score were standardized to improve giant descent speed and prepare for potential linear models and neural networks. And then we are talking about the feature engineering. First one is the age grouping. Ages were divided into young, mid-age, adult, and senior groups to capture behavioral differences across age segments. Second is the debt to income ratio. Loan amount divided by income reflecting the borrower's financial burden. Third one is the income per year of employment. Income divided by employment years plus one, representing income stability. Fourth one is the loan interest burden. Loan amount multiplied by interest rate, reflecting interest cost pressure. Fifth one is income to loan ratio. Income divided by loan amount, measuring the ability to repay the loan. Sixth one is the credit history length to age ratio. Credit history length divided by age, indicating credit accumulation relative to age. Last one is the employment experience to age ratio. Experience year divided by age, showing early or late employment onset. And here is the handling class imbalance. So due to the severe class imbalance in the dataset, we applied SMOT to balance the classes. This ensures that the model didn't overly favor that non-default class, effectively improving the F1 score. And here is the model comparison and assumptions. We evaluated various baseline models using stratified key fault cross-validation and selected the top-performing models based on the F1 score for final ensemble construction. The models considered were first one is the XGBoost, best perform, strong against overfitting, excels at capturing nonlinear relationships and evaluating feature importance. Second is the Light GBM, which is fast training, suitable for large datasets, particularly effective when there are many categorical features. Third one is the Random Forest, which is robust, strong in handling features interactions, but computationally intensive. Fourth one is Logistic Regression, which is linear model with high interpretability but limited in capturing nonlinear relationships. Fifth one is KNN, which is sensitive to distance metrics. Performance degrades in high dimensional spaces. Sixth one is the SVM, which is suitable for medium to small datasets but computationally expensive. Seventh one is the neural networks, which is effective for complex patterns but sensitive to parameters and training time. Last one is the decision trees, which is high interpretability but prone to overfitting.
To find out the best model, we tried top 3 and top 2 models to perform a voting model. As the result, the combination of XGBoost and LGBM scores better than added random forest. To further improve performance, we performed randomized search CV on XGBoost and LightGBM with iPhone score as the evaluation metric. Random search is more efficient than grid search in high-dimensional parameter spaces. The optimal parameter obtained are listed here. To post-tuning, the F1 score of both models improved significantly. To ensemble modeling and final selection, we tested following ensemble strategies. First is voting. After parameter tuning, we used a soft voting ensemble of XGBoost and LightGBM with a higher weight for XGBoost. It achieved an F1 score on 0.9963 on the test set, the highest among single models. However, its performance in five-fold cross-validation was slightly inferior to stacking, indicating potential sensitivity to specific data splits and lower generalizability. Next is stacking. Using the tuned XGBoost as the final classifier and the LIGBM as the base learner, stacking further improved performance. It achieved an F1 score of 0.9940 on the test site and was the most suitable in cross-validation. Thus, we selected stacking as the final model. For model evaluation and validation, we used stratified k-fold cross-validation to ensure that class proportions were maintained in each fold, reducing randomness. Five-fold were chosen as a practical balance between computational cost and stability. Further work should explore nested cross-validation to further avoid data leakage during parameter tuning. Upon deployment, the model should be monitored using F1 score, AUC, and other metrics on the incoming data. From the learning curve, we can observe that the F1 score on the training set is nearly perfect, while the cross-validation F1 score gradually improves as the number of training samples increases, eventually stabilizing above 0.9. This indicates that the model's generalization ability improves with more data, though there are slight signs of overfitting. This is expected as tree-based models like XGBoost are powerful and can easily fit the training data well. The ROC curve shows an AUC of 0.9999, which is close to perfect classifier. This suggests that the model performs exceptionally well in distinguishing between default and non-default customers. However, an AUC this high may also indicate potential data leakage or an overly strong signal in the data. Therefore, it is essential to validate the model's robustness in real-world applications and collaborate with business experts to fine-tune the decision threshold, balancing approval rates and default risks. Through feature engineering, class balancing, model selection, parameter tuning, ensemble learning, and cross-validation, we achieved an F1 score of 0.9940 with the stacking model on the test set, providing a robust solution for loan default risk prediction. For future work, we have several thoughts. First, integrating macroeconomic data and credit bureau information to enrich feature sets. Second, exploring Bayesian optimization and other advanced hyperparameter tuning techniques. And third, implementing dynamic threshold adjustments to optimize risk strategies for different customer segments. OK，可以了，不念了。